Okay, so let me try to recall where we are at this point of our discussion. So we have this region script D. Okay, so let me draw that. So you have, well, so this is the tau plane, and of course this is the upper half plane, and we take these points 0. This is the, of course this is the real axis, this is the imaginary axis. So you have the point half, and this is the point 1, and there is the point minus half, there is a point minus 1, and with 0 as the center, draw a semicircle of radius 1 in the upper half plane. So it will pass through I, and so you have this semicircle, and of course and of course we also take the vertical line passing through half, okay, which is well going to be like this, and we have the vertical line passing through minus half, which is well going to be like this, and the region script D is actually composed of these two interiors. Okay, this is we call this delta, we call this interior as delta prime. Okay, and we also add the boundary, but we take out a part of the boundary. We take out this vertical this ray, okay, and then we take out this arc of the semicircle, but we retain I. Okay, so this point, so these 2 points are this point corresponds to one complex cube root of unity. So this is so this point is 1 plus I root 3 by 2, and this is minus 1 plus I root 3 by 2, that is this point. Okay, and script D is so script D is this shaded region, and of course we don't include this this half line and this semicircular, I mean this piece of the semicircular arc. Okay, so maybe I'll just put I'll just make it a dotted line, so that so this is not included and this is not included. Okay, and then whatever we have, whatever is shaded is we called it script D. Okay, and the claim was we were trying to show that script D is a fundamental region for the unimodular group PSL2Z acting on the upper half plane, and we also wanted to show that script D is also a fundamental region for the modular function j tilde. Okay, so let me write that down. We are trying to show that script D is a fundamental region for number 1 PSL2Z, the unimodular group acting on the upper half plane, and number 2 j tilde defined from the upper half plane to C, which is PSL to Z invariant. Okay, this is what we are trying to show, and we are trying to show this because this will prove that the function that j tilde defines by passage to the quotient from u mod PSL to Z to C will turn out to be a bijective holomorphic map, and so it will be a holomorphic isomorphism. And so of course our aim has been to try to show that the Riemann surface structure on u mod PSL to Z is biholomorphic to the complex plane, okay, which has the interpretation that the set of isomorphism, holomorphic isomorphism classes of complex tori is identified with C as a Riemann surface, and the identification is done by a single invariant which is the j function, and the j function comes from passage to the quotient mod PSL to Z from j tilde, okay. So this is what we are trying to prove. So what we proved last time, we have already proved, we showed last time that what we showed was you take any PSL to Z orbit in U, it does intersect script D. This is what we proved last time, okay. We showed last time that any PSL to Z orbit in U does intersect D. What does it mean? It means give me any element in the upper half plane and you take image translates of that element by the elements of PSL to Z, that is apply on that element all possible unimodular Mobius transformations. You will get various other elements in the upper half plane, and all these elements put together will be the orbit of that element, and what we proved is that that orbit intersects D. So there is a point in D whose PSL to Z orbit is the same as any given PSL to Z orbit, okay. So this is what we proved last time. Now what we need to prove, what we will try to prove next is that we will show that that intersection is unique, namely that for every PSL to Z orbit there exists one and only one point of script D where it intersects script D, okay. So this will tell you that the script D consists of a full set of representatives of the orbits of PSL to Z on U. In other words, it will show you that the restriction of the quotient map from U to U mod PSL to Z, if you restrict it to script D, it will be bijective, okay. So so let us try to prove uniqueness, right. So we now show that such an intersection is unique, okay. So how does one do that? So we start with so what we will do is we will start with two elements in script D and assume that one is the image of another by an element of the unimodular group, okay. So they will both be points in a single orbit, PSL to Z orbit, which lie in D, script D, and then we will show that they are one and the same, okay. So let tau 1 tau 2 be in script D, and with tau 2 is equal to A tau 1 plus B by C tau 1 plus D, where AD minus BC is 1 and a b c d are integers. Okay. So what I have assumed is that this Mobius transformation, which is represented by the matrix a b c d with determinant 1 and is thought of as an element in PSL2Z, when that acts upon tau 1 you get tau 2. This is what I have assumed. So what I have assumed is tau 2 is the image of tau 1 under that element of PSL2C, namely the Mobius transformation defined by Z going to A Z plus B by C Z plus D. Okay, and of course the condition is AD minus BC is 1 and ABCD are of course integer entries, so that makes this an element of PSL2C, okay, a unimodular transformation. What I will have to show is that so that means the orbit of tau 1 is the same as the orbit of tau 2, they lie in the same orbit of PSL2Z, and all I have to show is that I have to show tau 1 is equal to tau 2. Okay, so we will look at various cases and prove this. So what we will do is, well, the first thing that that one needs to start with is so from this expression we will get an expression for imaginary part of tau 2. Okay, so you see imaginary part of tau 2 will be, well, if you calculate it, it will be imaginary part of tau 1 by modulus of C tau 1 plus D the whole square. You will get this expression. This is just by direct calculation. See, because the left hand side is imaginary part of tau 2, which is tau 2 plus tau 2 minus tau 2 bar by 2I. So this is going to be, well, plug in this expression for tau 2, so you will get A tau 1 plus B by C tau 1 plus D minus A tau 1 plus B by C tau 1 plus D the whole bar by 2I. This is what you will get, and that turns out to be, well, 1 by 2I. What I will get here is, of course I will get this complex number into its conjugate, so in the denominator I will get mod C tau 1 plus D the whole squared, this complex number into its conjugate, and the numerator I am going to get A. So if I calculate I will get A C bar mod tau 1 the whole squared, so it is A tau 1 into C bar tau 1 bar. Okay, so it will be A C bar tau 1 bar is mod tau 1 the whole squared, then I will get A tau 1 into D bar, A tau 1 times D bar, and then I will get B into C bar tau 1 bar, and I will get B into D bar. Okay, this is what I will get when I multiply this with this. Okay, and then I will get minus, well, minus same denominator C tau 1 plus D the whole squared. I have to multiply now this with this, I will get C A bar or A bar C into mod tau 1 the whole squared, and I will get D A bar D into tau 1 bar, and I will get B bar C tau 1, and I will get a B bar T. Okay, this is what I will get, and, well, I think I can cancel out a few terms. Can I? So I will have to make use of the fact that, of course I will have to make use of the fact that A, B, C, D are integers, so they are real numbers, so the the conjugates of A, B, C, D are A, B, C, D themselves, so you have to make use of that, and if you make use of that you can see that this term and this term will cancel, alright, there is a minus sign outside here, okay, and similarly this BD and this is BD, this is also BD, so that will also go, okay, and well I'll be left with AD into tau 1 minus tau 1 bar plus AD minus BC into tau 1 minus tau 1 bar. So I will simply get 1 by 2i tau 1 minus tau 1 bar into AD minus BC divided by mod C tau 1 plus D the whole squared, but of course AD minus BC is 1 and tau 1 minus tau 1 bar by 2i is imaginary part of tau 1. So it is just imaginary part of tau 1 by mod C tau 1 plus D the whole square. Okay, so that is how I get this, right. So why is this, so this helps us to reduce to a certain case. So you know, of course tau 1 and tau 2 are in the upper half plane, so the imaginary parts are positive. So I, without loss of generality, I will assume that say the imaginary part of tau 1 is say less than or equal to imaginary part of tau 2. I will assume that imaginary part of tau 2 is greater than or equal to imaginary part of tau 1. Okay, so we can assume without loss of generality that imaginary part of tau 2 is greater than or equal to imaginary part of tau 1 we can assume this. So that that amounts to assuming that mod C tau 1 plus D the whole squared is less than or equal to 1. Okay, from this expression it amounts to assuming that mod C tau 1 plus D the whole squared is less than or equal to 1. Okay, so of course what will happen if imaginary part of tau 2 is lesser than imaginary part of tau 1. So you just interchange the roles of tau 1 and tau 2. Interchanging the roles of tau 1 and tau 2 means you will have to write tau 1 in terms of tau 2, and when you write tau 1 in terms of tau 2 you will just write the inverse of this Mobius transformation, and the inverse will also be a PSL2Z elements, PSL2Z element, and instead of A B C D you will get some other coefficients A prime, B prime, C prime, D prime, and that will also be a PSL2Z element, and that will be the inverse of this. Okay, so there is no harm in assuming that imaginary part of tau 2 is greater than or equal to imaginary part of tau 1. There is no loss of generality. Okay, so we assume this. Now we will have to look at this carefully. So this is the same as saying mod C tau 1 plus D is less than or equal to 1. Okay, and well so we look at various cases. We look at cases when, specifically at cases when C is 0 and C is not 0. Okay, so let me follow what I have written down here. So yeah, so first we will assume case 1 C is 0 and of course case 2 will be C not equal to 0. Okay, so consider case 1 C is equal to 0. Okay, so if C is 0, what will happen is, if C is 0 you will get mod D is less than or equal to 1. Okay, you will get mod D is less than or equal to 1. On the other hand, you know, AD minus BC is 1, so C is 0 will tell me AD is 1. Okay, so AD minus BC equal to 1 will tell me that C, because C is 0 it will tell me AD is 1. Okay, mind you AD is 1, therefore D is not 0. Okay, so D is a non-zero integer with modulus less than or equal to 1, so it has to be modulus 1, it can be only plus or minus 1. So this implies D is not equal to 0, and this implies that D is just mod D is just 1. This implies mod so it implies d is plus or minus 1. So this is what you will get, okay, and then what happens then? Well, we will have so if you look at this expression, first of all I will get imaginary part of tau 2 is equal to imaginary part of tau 1, okay. So this will imply imaginary part of tau 2 be imaginary part of tau 1, you will get this, and well, you will also get what else, so I'll also get here tau 2, yeah, of course I should also write here when corresponding to d equal to plus 1 I will get a equal to plus 1, when d is minus 1 I will get a is minus 1, so I will get d is equal to 1, a is equal to 1, or d equal to minus 1, a equal to minus 1, these are the two cases I get. And well, then what happens of tau 2, so in this case tau 2 will be, well, if I put it here a is 1, so I will get tau 1 plus b, okay, divided by c is 0, d is 1, so I will get tau 1 plus b, so I will get tau 2 equal to tau 1 plus b, okay, and in this case I will get tau 2, well, if I plug in I will get tau 1 minus b, because I will have to put a equal to minus 1, okay, and I will have to put d also as minus 1, so I will get tau 1 minus b, okay. So so what I will get is basically I will get tau 2 equal to tau 1 plus or minus b, okay, this is what I will get corresponding to whether d is plus 1 or minus 1, but this will tell me that tau 2 minus tau 1 is plus or minus b, okay, and but then that is real, so this will also tell me that real part of tau 2 minus real part of tau 1, okay, is equal to plus or minus b, this is what you will get, and you see but you see there is a restriction on the real part of tau when tau is in d, okay, there is a restriction, so you see in fact that should tell you that b is actually 0, that is because you see the real part of any tau in the script d has to be greater than minus half and less than or equal to half, okay, and you take two such tau 1 and tau 2 there, the distance between them, okay, the distance between their real parts has to be strictly less than 1, okay. So what this will tell you is that this will tell you that if I take modulus of this, if I take moduli on both sides, you see this side is strictly less than 1, so the left side is strictly less than 1 and that will be strictly greater than the right side, okay, and b is an integer, so b is an integer with modulus strictly less than 1, okay, so it has to be 0, so this will imply b is equal to 0, and if you put it back here you will get tau 1 equal to tau 2, okay, so that disposes of the case when c is equal to 0, that is case 1, alright. So we will have to go to case 2, which is c is not equal to 0, c is not equal to 0. So if c is not 0, then I look at this inequality and I try to then I can divide by c, okay, what I will get is I will get mod tau 1 plus d by c is less than or equal to 1 by mod c, okay, since c is not 0 I can divide by c by mod c, okay, this is what I will get. And now again the claim is that mod c has to be less than or equal to 1, mod c has to be less than or equal to 1, okay, for otherwise mod c is greater than 2, okay, will tell you that modulus of tau 1 plus d by c is strictly less than half, okay. If mod c is less than or equal to 1, if it is not less than or equal to 1, that means mod c is greater than 2, 1 by mod c is less than 1 by 2, and therefore mod tau 1 plus d by c is strictly less than half. What does it say? If you go back to this diagram, it says that the distance of tau 1 from minus d by c is on the real line, because d and c are integers, non-zero integers, okay. So I mean c is non-zero, so distance of tau from the real line, from a point on the real line, it is less than half, okay. That can never happen, because you see the shortest distance of a point from script d to the real line is this, and that is root 3 by 2. See, this length is root 3 by 2, this is the shortest distance, okay, of a point of script d to the real line, and therefore you cannot have this inequality can never hold, okay. So which can't hold, which cannot hold as so let me write it here as the shortest distance of a point of script d from a point on the real axis is half, is root 3 by 2. The shortest distance is root 3 by 2, that is attained only at this point, not even at this point, because this point has been removed. So so this is the point which will have the shortest distance, and the shortest distance will be root 3 by 2, so it can never be half, so this can never happen. So the moral of the story is mod c is less than or equal to 1. So and c is of course not 0, so it means that mod c is 1, so c is plus or minus 1, okay. So c is equal to plus or minus 1, this is what you get, okay. And so what will happen is you will get if c is 1, then you will get mod tau 1 plus d is less than or equal to so c is 1 is less than or equal to 1, okay, you will get this, and if c is minus 1, then mod tau 1 c is minus 1 and mod tau 1 minus d is less than or equal to 1. This is what you will get. So let us try to interpret this. What this says is the distance of tau 1 to the integer d is less than or equal to 1, and this says the distance of tau 1 to the integer d, I mean, so this is the distance of tau 1 to the integer minus d, that is less than or equal to 1, and this says distance of tau 1 from the integer plus d is less than or equal to 1. So if you look at that diagram, okay, then see there are only few possibilities for d, okay. So tau 1 is somewhere here, okay. The first inequality says the distance of tau 1 from d is less than or equal to 1, okay. So see, of course d can be 0 or minus 1 or plus 1, alright, there are three possibilities, and of course if and you know if d is minus 2, okay, then the distance if d is minus 2 or if d is less than or equal to minus 2 or d is greater than plus 2, then the distance of d from tau is certainly greater than 1, okay. Therefore the only possibilities are d equal to 0, plus 1 or minus 1, okay. So what I want to tell you is that so d is only 0 or plus or minus 1, there are only three possibilities, okay, and so we will have to look at each of these cases, okay. So of course you know if So if you look at d equal to 0, then I can again use I can again use the fact that AD minus BC is 1, so I will get AD minus BC is equal to 1 gives BC equal to 1, okay, and well of course D is 0, I will get BC is equal to 1 and sorry BC is equal to minus 1, and yeah of course I should say before I said all this, see if D is 0, see the condition is mod tau 1 is less than or equal to 1, okay, and see mod tau 1 is less than or equal to 1, so that means tau 1 is in D and the distance of tau 1 from the origin is less than or equal to 1, so it means it is actually equal to 1, okay, and it means that it has to lie only on this semicircular arc, so that is a deduction that we have to do, okay. So you see, so I should say here so even before I write this I should say also mod tau 1 has to be 1, okay, and real part of tau 1 is greater than or equal to half, okay, and of course real part of tau 1 is also supposed to be less than or equal to no what I want to say is real part of tau is greater than or equal to 0 and less than or equal to half, yeah, so I should say it is greater than or equal to 0 and less than or equal to half. So you see tau 1 is lying here on this semicircular arc, okay, that's what it says. I will have to make use of this, you see C is so you know here C is plus or minus 1, D is 0, so this is just mod tau 1 the whole squared, okay, and that is 1, so I will get imaginary part of tau 2 is equal to imaginary part of tau 1, so in fact I will also get so that is the main point. So imaginary part of tau 2 is equal to imaginary part of tau 1, this is what I will get. So in this case we will essentially show that tau 1 and tau 2 are equal, they are equal to I, okay. So let us compute what tau 2 is. Tau 2 is by our assumption it is a tau 1 plus b by c tau 1 plus d, and our d is 0, so I will get a tau 1 plus b by c tau 1 which is a by c plus b by c tau 1, and this will turn out to be, if I put the choices for c are plus or minus 1, so if I put c equal to plus 1, if I put c equal to plus 1 then b is minus 1, so I will get a by 1 plus b is minus 1 by 1 into tau 1, and this is going to give me a minus 1 by tau 1. If I put c equal to minus 1 then I will get b equal to 1, so I will get a by minus 1 plus 1 by minus 1 times tau 1, this is going to be minus a minus 1 by tau 1. So in all put together you get tau 2 equal to plus or minus a minus 1 by tau 1, okay. So tau 2 plus 1 by tau 1 is equal to plus or minus a, okay. Now so you see the so interpret it as well, if you take modulus of tau 2 minus 1 by tau 1, I will get mod a, okay, and this mod a is an integer, okay. So this claim is a is actually 0, okay. First of all minus, so tau 1 is here, tau 1 is somewhere on this arc, okay. So minus 1 by tau 1 is therefore on this piece of the arc, okay, and tau 2 is somewhere else, and maybe I should have taken before taking the modulus I should have taken real part and then I should have taken modulus. So in fact what I will do is instead of taking, so what I will do is at this point let me first take real part. So I will have real part of tau 2 plus real part of 1 by tau 1 is plus or minus a, and now I take modulus. I will get real part of tau 2 minus real part of minus 1 by tau 1 is equal to mod a, okay. And now you see so tau 1 is here, minus 1 by tau 1 will be its reflection here, and tau 2 is somewhere in this region in script d, and if you take the real parts, okay, and you want the distance between them to be equal to an integer, alright, and therefore the only possibilities are either the distance can be 1 or it can be 0, okay. So if so you see a is 1 or 0, okay, and what I want to say is I want to rule out the case when a is 1, when if a is 1 then I will have they have to see, if a is 1 then they have to lie on these two vertical lines, okay, and 1 is here, so if so that means and of course I also have imaginary part of, so I also have imaginary part of tau 1, of course I also have imaginary part of tau 1 is equal to imaginary part of tau 2. I mean the only possibility is that one of them is 1 plus I root 3 by 2 and the other is minus 1 plus I root 3 by 2, okay. A equal to 1 means tau 1 has to be 1 plus I root 3 by 2 and tau 2 is minus 1 plus I root 3 by 2, but then tau 2 is not in D because this has been removed from D. So so A is not equal to 1, so A is 0, okay, and if A is 0 of course this will tell you that tau 2 is minus 1 by tau 1, and you will also get mod tau 2 is equal to 1 by mod tau 1 which is 1, so you will get mod tau 2 is also 1, and combined with the fact that tau 2 and tau 1 have the same imaginary part will so imaginary part of tau 1 is equal to imaginary part of tau 2 will tell you that tau 1 is equal to tau 2 is actually equal to I, okay. So that settles the case when D is 0, okay. Now we will have to look at the case when D is plus or minus 1, okay. So the point is that when if in the subcase when C is not equal to 0, D equal to 0 corresponds to the tau 1 equal to tau 2 equal to I, okay, and D not equal to 0 which means D is equal to plus or minus 1 will correspond to tau 1 equal to tau 2 equal to 1 plus I root 3 by 2, that is what we have, that is what we will show essentially, okay. So so let me look at that case also. So I will have to look at if D is equal to plus or minus 1, okay, then I will have so I also have C is equal to plus or minus 1, okay, and of course I have both of these. So if C equal to so if you go here, C equal to 1 corresponds to mod tau 1 plus D is less than or equal to 1, so I will get C equal to 1 corresponds to mod tau 1 plus yeah, so I will get mod tau 1 plus or minus, so D is plus or minus 1 is less than or equal to 1, and C equal to minus 1 also will give, I guess will give me the C equal to minus 1 will also give me mod tau 1 plus or minus 1 is less than or equal to 1. so in any case the condition I have to look at is mod tau 1 plus or minus 1 is less than or equal to 1. So you look at two possibilities, mod tau 1 plus 1 is less than or equal to 1 and mod tau 1 minus 1 is less than or equal to 1. Okay, so what does this tell you? This tells you distance of tau 1 from minus 1 is less than or equal to 1, is at most 1. So here is my, so tau 1 is there somewhere in D, it is distance from minus 1. Okay, that distance has to be less than or equal to 1. Well, of course, you know, if I draw a circle centered at minus 1, radius 1, okay, it will pass exactly through this. Okay, so that means that the only solution is tau 1 is this, but that is not possible. Okay, so this implies that tau 1 is minus 1 plus I root 3 by 2 which does not belong to script D. So this case is not correct, this case will not occur. Okay, and if I take this case, this says distance of tau 1 from 1 is less than or equal to 1, so you know this means that tau 1 has to be 1 plus I root 3 by 2. Okay, so this will give me tau 1 is equal to 1 plus I root 3 by 2. Okay, and then I will have to say that tau 2 I will also have to say that tau 2 is equal to tau 1. Okay, so for that what I will have to do is maybe look at what I have assumed in this case. Yeah, if I look at the imaginary parts, yeah, in fact, see, if if tau 1 is this, then this quantity is actually equal to 1. So this implies that mod tau 1 minus 1 is actually equal to 1. Okay, and then now if you calculate the imaginary part of tau 2 is actually imaginary part of tau 1 divided by mod c tau 1 plus d the whole squared, and in this case I am going to get so this is 1. Okay, so this is exactly equal to imaginary part of tau 1. Okay, so what you will get is tau 2 and tau 1 they have the same imaginary part. Okay, and the imaginary part is root 3 by 2. Okay, there are only two I mean the only solution to that is that tau 2 is also equal to 1 plus I root 3 by 2, because this is the only this is the only point in script D whose y coordinate is root 3 by 2. Okay, so that will tell you that, so in fact so imaginary part of tau 2 is imaginary part of tau 1 which is equal to root 3 by 2, but there is only one tau in script D with imaginary part root 3 by 2, so this will give you tau 1 equal to tau 2 is equal to 1 plus I root 3 by 2. So as a result we have proved that there is only one orbit, I mean there is only one representative for each orbit in script D. Now the so what we have proved is that script D is a fundamental region for PSL2C. Okay, our definition of fundamental region was it should be an open set along with a part of the boundary which contains exactly one representative of each orbit and such that the translates of this by the elements of the group which is PSL2C should cover the upper half plane. Okay, that we have already checked. All right, so this completes the proof that, so this implies that there exists unique representative of each PSL2Z orbit of U of the upper half plane in script D. Okay. Now in other words, script D is a fundamental region for PSL2Z. Alright. Now the next step I'll have to show is that for J tilde also the script D continues to be a fundamental region. Alright, and so what one can tell immediately is that so you have to prove J tilde restricted to the script D is both injective as well as surjective. Okay, again the surjectivity part is immediate. Okay, the hard part is the injectivity part. So so let me write this down. Yeah, thus script D is a fundamental region for PSL2Z. Note also that J tilde restricted to script D is surjective. See, we have to prove that script D is a fundamental region for J tilde, so you have to show J tilde restricted to script D is both injective and surjective. I am saying surjectivity is immediate because you see, why is that true? That is because J tilde we know is already surjective. So there is some and if you remember that was proved using fundamental theorem of algebra. Okay, and so J tilde is already surjective on the upper half plane. Okay, so there is a point given any value J tilde will take that value at some point in the upper half plane, but then I can take the orbit of that point that will have a unique representative in script D, and the value of J tilde there will still be the same because J tilde is PSL2Z invariant. Therefore I can always, given any value, complex value, I can always find a point in script D where J tilde takes that value. Therefore J tilde restricted to D is surjective. Okay, so let me write that down. For given J naught in C, there exists tau in U such that J tilde of tau is J naught. We had already shown J tilde is surjective. Okay, but the PSL2Z orbit of tau has a unique intersection with D at a point where J tilde continues to take the value J naught as J tilde is PSL2Z invariant. Okay, so the moral of the story is that we are able to show that J tilde restricted to D is surjective immediately. The harder part is to show that J tilde restricted to script D is injective. So we will do that in the forthcoming lecture.